There is a waiting list for the most powerful telescope ever launched into space. Research teams spend years preparing proposals, compete against thousands of other scientists, and most of them still get rejected because there simply aren't enough hours in the sky for everyone who wants them. The James Webb Space Telescope is so oversubscribed that getting approved feels closer to winning a lottery than submitting a research paper. So when the European Space Agency contacted Webb's directors in February of 2025 and told them to cancel whatever was currently scheduled to physically repoint the telescope away from whatever distant galaxy or dying star it had been studying and aim it at something inside our own solar system instead, it meant something had gone seriously wrong closer to home. The object they needed Webb to look at was a rock roughly the size of a 10-story building, tumbling silently through the dark, about 7 years away from potentially ending a city. And the reason they needed Webb specifically, rather than any of the dozens of powerful ground telescopes already watching it, is because every single one of those ground telescopes had just told them the same thing. We cannot figure out how big this rock actually is. And until we know that, we cannot tell you whether to worry or not. This is the full story of Asteroid 2024 YR4. Not the version that made headlines for 2 weeks and then vanished from the internet. The version that took 18 months to actually finish playing out involved 2 separate emergency uses of the most expensive scientific instrument humanity has ever constructed and ended in a way almost nobody heard about because by the time the real answer arrived, the world had already stopped paying attention. Before we go any further, subscribe if this is the kind of deep dive you came here for, because this story has layers that most channels never got to. Let's get into it. It started the way most of these stories start, quietly. On December 27th, 2024, a network of automated telescopes called Atlas flagged a faint dot of light moving against the background stars in a pattern that didn't match anything in existing catalogs. Atlas stands for Asteroid Terrestrial Impact Last Alert System, a name that sounds dramatic until you learn the reason it exists. In 2013, a rock roughly 20 meters wide entered the atmosphere above Chelyabinsk, Russia, completely undetected. No telescope saw it coming. No warning system flagged it. Nobody on the ground had any idea it was there until it detonated in the atmosphere with the force of 30 Hiroshima bombs blowing out windows across the region and injuring over 1,000 people with flying glass alone. The entire encounter, from invisible to impact, lasted seconds. It entered from the direction of the sun, the one angle that ground-based telescopes cannot monitor because the sun's glare drowns out everything in front of it. That single blind spot turned a 20-meter rock into a completely invisible threat until it was already burning through the atmosphere. Atlas was built specifically so that could never happen again without at least some advance notice. It runs a small constellation of telescopes positioned across both hemispheres so that on any given clear night, at least one of them is scanning overhead, photographing the same patches of sky over and over and comparing frames to find anything that moved between exposures. It catches thousands of objects every year. The overwhelming majority of them are harmless, their orbits quickly calculated and confirmed to miss Earth by comfortable margins. They get logged into a database, assigned a name, and forgotten by everyone except the handful of professionals whose job it is to keep the catalog current. This one was named 2024 YR4, and it did not behave the way most new discoveries behave. Within a few weeks of its discovery, orbit calculations gave 2024 YR4 a small but notable probability of colliding with Earth on December 22nd, 2032, about 1%. On its own, that number would barely have registered. 1% impact probabilities show up regularly and almost always collapse to zero within days as additional observations tighten the math. Astronomers who track near-Earth objects for a living are trained to expect exactly that pattern. Flag, calculate, refine, clear, the rhythm of the job. But as January turned into February and more telescopes around the world contributed observations, something unusual happened. The probability didn't collapse. It climbed. By late January, it had reached 1.2%. By mid-February, 2.1%. And then on February 18th, 2025, NASA's Center for Near-Earth Object Studies briefly listed the impact probability at 3.1%, the highest number ever officially recorded for any asteroid in the size range capable of destroying a city. Now, here is the part of this story that almost every headline written at the time got wrong, and it matters because getting it wrong is exactly how a legitimately uncertain scientific situation turns into either manufactured panic or false reassurance, neither of which helps anyone. Rising odds in the early days after an asteroid discovery do not usually mean the danger is actually growing. They mean the uncertainty is shrinking. When a new object is first spotted, astronomers have only a handful of observations to work with, enough to sketch a rough path forward, but that path isn't a single line. It's a wide band of possible trajectories fanning out into the future like a cone of light from a flashlight. Earth is one small target sitting somewhere inside that cone. If, as more observations come in and the cone narrows, Earth happens to be sitting near the center of the shrinking band rather than near its edge, the calculated probability rises. Not because the rock moved closer to hitting us, but because the math now has fewer places to put it that don't include us. The odds keep climbing right up until the band gets tight enough to either land squarely on Earth, which almost never happens, or squeeze Earth just outside its boundary entirely, which is what happens nearly every time. Think of it like focusing a blurry photograph. The image gets sharper and sharper, and for a while, the thing you were worried about looks bigger and clearer and more real, right up until the final adjustment snaps it into focus and you realize it was never actually in front of you. It was a few feet to the left the whole time. That is exactly what happened here. But nobody knew that yet in mid-February. At 3.1%, 2024 YR4 had climbed to a 3 on the Torino scale, a standardized system designed to communicate asteroid risk to the public and to governments in plain language. The scale runs from 0, meaning no hazard whatsoever, through 5, meaning a serious and credible threat requiring governmental attention, all the way up to 10, a certain collision capable of triggering a global catastrophe. A rating of 3 is defined specifically as a close encounter, deserving of sustained attention from astronomers, not yet warranting public alarm, but serious enough that continued monitoring is considered essential. No asteroid in the history of modern planetary defense had ever reached 3 and stayed there before. Most objects that briefly touch a 1 or a 2 drop back to 0 within days as new observations come in. Reaching 3 and holding meant that more data was sharpening the problem rather than dissolving it. This was entirely new territory. And this is exactly where the European Space Agency made the call that opens this story. They requested directors' discretionary time on the James Webb Space Telescope, a small reserve of observing hours held back from the normal proposal process, specifically for situations where waiting for a committee to review and approve a request would mean missing the observation entirely. It gets used only a handful of times per year. Requesting it means telling the telescope's directors in real time that your target is more urgent than whatever research other scientists spent years competing to schedule. Nobody enjoys making that argument. In this case, nobody had a choice. The reason Webb was irreplaceable came down to a single technical limitation that every ground-based telescope shares. When you observe an asteroid from Earth, you see it by the sunlight bouncing off its surface. That reflected light tells you the object exists and where it is, but it tells you almost nothing reliable about how large it actually is. A small, highly reflective rock and a large, dark one can bounce back the exact same amount of sunlight toward Earth, making them functionally indistinguishable through any ground-based instrument. The estimated size range for 2024 YR4, based on ground observations alone, spanned from roughly 40 meters to 90 meters across. That is not a minor gap. A 40-meter object striking a populated area would cause severe localized damage across a few city blocks. A 90-meter object would flatten everything within a radius of several kilometers. Those are fundamentally different conversations requiring fundamentally different responses, and no telescope on the ground could tell you which conversation you were actually in. Webb doesn't see reflected sunlight, it sees heat. Infrared radiation emitted directly by the asteroid itself, regardless of whether its surface is bright or dark, shiny or matte. One set of Webb observations could collapse that entire ambiguity range in a way that no ground telescope, no matter how large or well-positioned physically could. While the request for emergency time was still working its way through approval, the ground-based picture started improving on its own. On February 19th, the impact probability dropped to 1.5%. The following day, it fell again to 0.27%. By the end of February, the 2032 Earth impact had been effectively ruled out, and the Torino scale rating dropped to 1, then eventually to 0. The uncertainty band had finally squeezed Earth outside its edges. The photograph had finished focusing. The danger had been somewhere off to the left the entire time. Most media coverage stopped right here. Headlines moved on. The asteroid was cleared, crisis over, story done. Reporters who had breathlessly called 2024 YR4 a city killer for 2 weeks quietly filed their last updates and turned to other things. The phrase city killer itself deserves a closer look, because while it technically describes the right size class of object, it dramatically overstated the actual risk at every stage of the story. An object in the 50 to 70 meter range striking a heavily populated urban center directly could indeed cause catastrophic localized destruction, comparable in some estimates to the 1908 Tunguska event over Siberia, which flattened roughly 2,000 square kilometers of remote forest. But the odds of any given impact actually landing on a city rather than on ocean, desert, farmland, or wilderness, which together cover the overwhelming majority of Earth's surface, were never part of the headline math. NASA's own communications, by contrast, stayed carefully measured throughout, repeatedly noting that even at 3.1%, the far more likely outcome by a wide margin was still a clean miss. The gap between how the story was reported and how the science actually read is worth remembering, because it is exactly the gap that turns a real, legitimately uncertain scientific story into either panic or premature reassurance, when the actual honest answer sat somewhere specific and calculable in between the whole time. But none of that matters nearly as much as what happened next, because the story was barely half finished. Webb's emergency observations went ahead in March of 2025 anyway, not because Earth was still at risk, but because the telescope had already been scheduled, and the scientific value of measuring this object's true size hadn't disappeared just because the threat had. The results came back precise. 2024 YR4 measured between 53 and 67 meters across, narrowing the ground-based estimate by more than half and settling a lingering dispute about how reflective the surface actually was. A clean, definitive measurement from an instrument capable of resolving exactly the kind of ambiguity that had kept the real answer out of reach for months. And then something happened that nobody had been anticipating. With the size confirmed and Earth definitively safe, astronomers turned their refined orbital model toward a different question, almost as an afterthought. If the asteroid wasn't going to hit Earth on December 22nd, 2032, where exactly would it be on that date? The improved calculations, incorporating Webb's March data alongside months of ground observations, revealed something the earlier, blurrier estimates had missed entirely. There was now a measurable chance the asteroid would strike the moon instead. The initial lunar impact probability sat around 1.7% before Webb's data arrived. After the March observations, it jumped to 3.8%. Then in June 2025, Webb captured one final observation of the asteroid before it faded too far and too faint for any instrument to track, its last usable data point before the rock was expected to swing back into view sometime in 2028. That final observation pushed the lunar impact probability to 4.3%. One chance in 23 that a 60-meter rock would slam into the moon on a known date roughly 7 years in the future. A moon impact wouldn't shift the lunar orbit. The mass difference between the two bodies is measured in trillions. It wouldn't directly threaten anyone on Earth's surface, but the moon isn't empty anymore. Multiple nations and private companies have hardware on or orbiting the lunar surface as part of a growing wave of exploration activity building toward permanent installations near the South Pole. An impact of this magnitude would throw up a debris plume potentially visible from backyards on Earth, with a genuine risk to any surface infrastructure or orbital assets anywhere near the strike zone. It would also be something unprecedented in human experience, the first time our species would watch on a known date with advanced preparation as a sizable asteroid struck another world. The most thoroughly documented crater formation event in recorded history, if it happened at all. And beyond the scientific windfall, there were practical diplomatic questions nobody had ever needed to ask before. If a known impact is coming to the moon, who decides whether to attempt a deflection? Who pays for it? Whose infrastructure takes priority? These weren't abstract hypotheticals anymore. They were questions with a 4.3% chance of needing real answers on a real timeline. And then the asteroid vanished. From June 2025 onward, 2024 YR4 was too far and too dim for any telescope on Earth or in orbit to observe. Its predicted return into detectable range wasn't expected until 2028. For the better part of a year, that 4.3% figure sat untouched in official databases while the rock itself drifted somewhere along a trajectory that existed only in equations nobody could currently verify against reality. A genuine, open question with real stakes attached and no way for anyone on the planet to check the answer for years. Not because anyone was withholding information or suppressing results, but because the laws of physics had simply made the object invisible. It was too far away and too small to reflect or emit enough light for any instrument currently in existence to detect. The universe itself had drawn a curtain across the answer and wouldn't lift it again until the rock's orbit carried it back close enough to see. That wait was supposed to last until 2028. It didn't. In February of 2026, an international team led by astronomer Andy Rivkin at the Johns Hopkins Applied Physics Laboratory found two narrow windows where Webb might still detect the asteroid years ahead of schedule. The trick depended on a European space mission called Gaia, which has spent the past decade mapping the precise positions of nearly 2 billion stars. If Webb could catch 2024 YR4 drifting across a field of Gaia-cataloged reference stars at exactly the right moment, astronomers could pin down its position against those known points with extraordinary accuracy, even with the asteroid itself barely registering as a detectable signal. The team had to identify not just when the rock would be theoretically bright enough to catch, but when it would coincidentally pass through a background field containing enough reference stars to make the measurement possible. That alignment happened exactly twice within the available window. Two chances. Miss both, and the world would be waiting until 2028 for answers just as originally expected, with a 4.3% lunar impact probability sitting unchallenged in the official record for another 2 full years. On February 18th and February 26th, 2026, Webb attempted the observations and captured the faintest confirmed detection of a near-Earth object in the telescope's operational history. On March 5th, 2026, NASA announced the result. Asteroid 2024 YR4 will pass the moon at a distance of roughly 21,200 kilometers, give or take about 800, safely outside any possibility of impact. The 4.3% chance was gone. NASA extended the same refined orbital model out a full century and found no meaningful impact risk to Earth across that entire span either. The official collision probability for the 2032 encounter now sits at approximately 1 chance in 20,000, a number so small it formally ends the conversation in planetary defense terms. So that's the ending. Clean, definitive, quiet. Almost nobody heard it. But the ending is not the point. The point is what the entire 18-month episode proved about the system built to handle exactly this kind of situation. Because there is a version of this story where the outcome is different, and it is the only reason any of the infrastructure described here exists at all. In September of 2022, NASA deliberately crashed a spacecraft called DART into a small moonlet named Dimorphos to prove that humanity could physically redirect an asteroid's orbit given enough advance warning. The mission worked. Models had predicted the impact would shorten Dimorphos's orbital period by about 7 minutes. The actual result came back at over 33 minutes, more than 4 times larger than expected, because the collision ejected a massive plume of debris whose own momentum added to the push far beyond anyone's models. Even a mission that engineers spent years designing, testing, and rehearsing delivered a result nobody had fully anticipated. That gap between prediction and outcome matters here, specifically because it is a reminder of how much uncertainty still exists in our understanding of how asteroids behave when you interact with them physically. Every model is an approximation. Reality retains the right to surprise you. That mission proved we can push a rock off course. What 2024 YR4 tested was something different and arguably more important, whether we could see a rock clearly enough, quickly enough, to know whether pushing it off course would ever become necessary. That test is exactly what nearly failed in those first uncertain weeks of February 2025 and exactly what succeeded 18 months later. The entire pipeline, from automated discovery through international data sharing, through honest public risk communication, through emergency deployment of humanity's most advanced instrument, performed under real pressure for the first time and delivered a definitive answer. That matters because it is worth being honest about the part of this story that is not reassuring, since pretending otherwise would undersell what actually happened. For several weeks in February 2025, professional astronomers using the best available data genuinely could not rule out a roughly 3% chance that a city-scale impact was 7 years away. That uncertainty was not manufactured for clicks. It reflected the real current limits of how quickly humanity can characterize a newly discovered object using ground-based telescopes alone. Closing that gap required an instrument so powerful and so oversubscribed that using it for this purpose meant physically taking it away from other scientists who had waited years for their own chance. Twice. The European Space Agency is already building toward the next chapter, a planned mission called NEOMIR, a dedicated infrared space telescope designed to spot objects like 2024 YR 4 years earlier than ground-based systems can, specifically by watching the one direction ground telescopes physically cannot cover. Asteroids approaching from the sunward side of Earth's sky are invisible to surface instruments hidden in the glare the same way you can't spot a bird flying directly in front of the sun. NEOMIR, positioned at a stable gravitational point between Earth and the sun, would close that blind spot entirely, potentially adding years of critical warning time to any future object following the same kind of sunward approach path, time that could mean the difference between a deflection mission launched comfortably and one launched too late to matter. Meanwhile, the Vera Rubin Observatory in Chile has begun its own decade-long sky survey expected to catalog tens of thousands of previously unknown near-Earth objects in exactly the size class that 2024 YR4 occupies, objects large enough to devastate a region but small enough to hide until they wander close for the first time in their entire orbital history. Current estimates suggest the vast majority of asteroids in this range remain undiscovered. Each one is a future February 2025 waiting to happen, with potentially less warning time attached. That means more headlines like this one are coming, not fewer, and that is not a sign the system is failing. It is the system working as designed, finding the rocks early enough that a 3% scare in February can resolve into a settled answer by the following spring instead of arriving with zero warning at all. What we know sitting here in the summer of 2026 is that a telescope built to photograph the formation of the first galaxies in the universe spent portions of 2 consecutive years pointed at something far less grand, a 60-meter rock tumbling through the dark on a collision course with nothing at all as it turned out, but close enough to something for long enough that no one involved could relax until the math finally and irrevocably said they could. Webb didn't discover a catastrophe. It discovered the absence of one with enough precision to make that absence trustworthy, which is the kind of result nobody wants to need and everybody is quietly grateful to receive. None of what happened over those 18 months worked because a single institution planned it flawlessly from the beginning. It worked because a Chilean telescope network built after a previous failure caught the object early. Because observatories on multiple continents, at least 50 different facilities by some counts, kept contributing data as the orbit sharpened week by week. Because 2 different space agencies agreed without public drama that a rock with a meaningful chance of hitting Earth deserved to jump the queue ahead of scheduled science. And because the same telescope got asked to solve the same problem twice, a year apart, and delivered a definitive answer both times. The next rock is already out there somewhere, unnamed, uncatalogued, following an orbit no one has mapped yet. It does not get to choose whether the system built to find it is ready when it arrives. That part is up to the people building that system right now, in observatories most of the world has never heard of, running instruments that only make headlines when the math briefly says something no one wants to hear. If someone in your life still thinks 2024 YR4 is a live threat because the internet has a habit of freezing stories at whichever headline arrived first, send them this. The ending exists. It just took 18 months, 2 emergency deployments of the most powerful telescope in human history, and a trick involving 2 billion precisely mapped stars to get there. Drop a comment if you ever heard the follow-up about the moon, because that part got almost no coverage compared to the original scare.